Welcome to Module 5 on momentum impulse method for particles. So we will see in this module that there are certain kinds of problems, especially involving collisions and impact, where applying momentum impulse method actually helps you solve problem much more easily. So take for example two particles, and let's say these two particles collide against each other. So before the impact they were traveling with some velocity. Let's call them VA minus and VB minus to indicate that these are the velocities before impact, and then after impact they're traveling with velocity, let's say VA plus and VB plus. So plus indicates post impact and minus indicates pre-impact. So some of the questions that we may have to answer are, if we know what the velocities are before the impact, what are the velocities of the particle after the impact? And impact and collisions are seen all around us all the time. When you play a ball game, let's say you play baseball or soccer or tennis or ping pong, there is a ball that hits against the racket or the bat. There is some pre-impact velocity, and you may be interested in finding what the post-impact velocity is. And you know that the material property of the surface against which the ball strikes can make a difference in what the post-impact velocity would be. Similarly, when you are driving a car or a truck, let's say there's an accident, the two cars collide against each other, there is a crash, and there is some debate as to what the speeds of the car might have been before the impact. Then there are people called collision reconstructors who come in and they can look at the current positions of the car after the impact, where they are, what their condition looks like, what their track marks are, and they can actually figure out what the pre-impact velocities might have been. So what we are going to learn in this module is going to be incredibly useful for figuring out answers to some of these kinds of questions. So just as we had learned in the previous module, which was module 4 on work energy approach, in this module we are going to relate some quantities of interest. So you will recall that in the work energy approach, the three quantities of interest were forces, displacement, and velocity. So we've seen that the work done by a force is equal to change in kinetic energy. Change in kinetic energy was defined as 1/2 mv final square minus 1/2 mv initial square, and the work done itself was given as integral f dx. So you can see we have force, we have the displacement, and we have the velocities over here. So these were the three primary quantities of interest that we could relate with each other, and we could answer questions like, if we know the change in kinetic energy, can we compute the force done on a particle or the distance traveled by a particle, or if we know the work done, maybe we can compute how the kinetic energy would change over time. So in this module, the three primary quantities of interest are forces, time, and velocity. Just as in the work energy approach, we had forces, displacement, and velocity, for the momentum impulse method for particles, we will see that the three primary quantities of interest are forces, time, and velocity. So there is no displacement over here, which means that in the problems where there is not appreciable movement of particles, but there is a force applied on the particle, and there is a change in velocity, and there is a time interval involved, we will see that this particular method is actually more suitable to solve the problems. Now, just as with the work energy approach, we started with the sigma F equal to ma, Newton's second law. We start with sigma F equal to ma for this method as well. So that tells you that this particular method is just a restatement of Newton's second law. Okay, so it's not like that we are creating a new principle in this module, or as we did in the previous module on work energy approach. So sigma F equal to ma, of course, we know that this has to be applied in an inertial or a Newtonian reference frame. We can write the right hand side as mass times d over dt of velocity. And if the mass is constant, which is what happens in a closed system, so closed system is defined as a system where the mass of the system, which could consist of multiple particles, doesn't change, then we can also write this as d over dt of mass times v. Right? So what we're saying is that mass is constant. If mass is not constant, it's changing over time, then these two quantities will not be equal to each other. Okay, so this quantity m times v is defined as linear momentum. Mass times v is defined as linear momentum. Okay, so sigma f can also be written as the rate of change of linear momentum, or p dot. Okay, so this is another form of Newton's second law. So instead of saying sigma f equal to ma as in Newton's second law, you can also say that sum of the forces applied on a particle is equal to rate of change of its linear momentum. So this gives rise to the principle of conservation of linear momentum, which is obtained if sigma f is equal to 0. So if some of the external forces acting on a particle are 0, then p dot is equal to 0, which implies that p is constant. And this is called conservation of linear momentum principle. So in the absence of any external force, we say that the linear momentum of a particle is conserved. Now, if mass is constant, that's also saying that velocity is constant, right? Which is exactly what we have seen before in the module 3 when we discussed the kinetics of particles, which said that if sigma f equal to 0, then acceleration is 0, which means velocity is 0. So it's not like that we are telling anything new over here compared to kinetics of particles module. It's just that we are stating it slightly differently. Now, this principle of conservation of linear momentum is particularly important when you have multiple particles. So let's say we have a system of particles. So a system of particles is basically multiple particles. It could be 2 particles, n particle, doesn't matter. All right. And on each particle, let's say there is an external force acting Fi, and this is Pi. And then there are multiple internal forces, which we'll write as Fij. Okay. So Fi1 would be the force from particle 1 on Pi. Fi2 would be force on particle Pi from particle 2, and so on. All right. But Fi over here is sum total of all the external forces acting on an individual particle. And we have seen that we can apply Newton's second law to individual particles. So sigma f on the I is equal to mi times its acceleration, and sigma fi itself is all the external forces, which are Fi, plus sigma Fij. Okay, those are internal forces. So this is external, and these are internal forces. And since there are more than one particles, that's why we have a summation over here. And the right hand side is mi times vi dot, right? Rate of change of velocity, which is nothing but acceleration. And we can write this equation for all the particles and add them together. So if we add them together, we have already seen that all the internal forces, since they occur pairwise, equal in magnitude but opposite in direction, they cancel out. And what you're left with are, on the left hand side, sigma fi, which is sum of all the external forces. And on the right hand side, we will get sigma mi times vi dot, right? So we are left with this equation, which says sigma f, and I will write ext here in the subscript to indicate these are sum of all the external forces, equal to sigma mi vi dot. Again, if this is a closed system, then this can also be written as d over dt of sigma mi vi, right? Because mass is constant, which is nothing but d over dt of sigma pi, where pi is the linear momentum of particle I, right? So we sum total all the linear momentum vector quantities and add them together and take their derivative, and that's the right hand side. So this form is similar to what we saw before for an individual particle. This was the equation for one particle, and this is the equation for a system of particles, and the equations are fairly similar. On the left hand side, we just add together all the external forces acting on the system, and on the right hand side, we sum total all the linear momentum vectors, and then we take their derivative, right? Again, we can create a principle of conservation of linear momentum for system if we say that sigma f external is 0. That implies that sigma pi is constant. So what this is saying is that if there are no external forces acting on a system, and how would you find that? You will draw a free body diagram. There's no skipping free body diagram in dynamics class. You would conclude from the free body diagram that there are no external forces acting on the system, and that means that the sum total of the linear momentum would be constant. Now, if the momentum of the system is constant, that doesn't mean necessarily that the momentum of individual particles would be constant as well. Okay, so if you can say that the conservation of linear momentum principle applies to a system, that doesn't necessarily imply that it applies for individual particles as well. Okay, of course, if principle of conservation of linear momentum applies for all the individual particles in a system, if you add them together, you will obtain this statement for the system as well, which will be true as well. Okay, all right. So we know that we can conserve the linear momentum if there are no external forces acting on the system, and we'll look at a few examples of this pretty soon. One more thing that I want to introduce here is the concept of linear impulse. Concept of linear impulse. What is that? We know that sigma f is equal to d over dt of m times v. Okay. If I take dt on the left hand side, I get sigma f times dt equal to dmv. All right. And if I integrate it on both sides, I get sigma f dt equal to change in linear momentum. So this would be mv final minus mv initial. So v final is the final velocity and initial, this vi is the initial velocity. Okay, so what this is saying is that if you know some of the forces and you know how they vary over time, then you can integrate it with time and then get the change in linear momentum as a result. Okay, this particular quantity over here is called linear impulse. The reason it's called linear impulse is because there's something called angular impulse too. Sometimes when people say simply impulse, they actually mean linear impulse. Just as for the momentum, you know, when people say linear momentum, that's being precise, but sometimes people say simply momentum and they actually mean linear momentum. So when you want to talk about angular momentum or angular impulse, you definitely say angular momentum or angular impulse. All right. Okay, so this quantity is called linear impulse, and that is equal to change in linear momentum. Now, if you know f, sigma f or f, let's say, as a function of time, let's say we are given t square I hat, you know, this is an example, minus 2tq j hat newtons. So if you know the function of the force, so, you know, it might look something like this. That's f on the y-axis. And the time is on the x-axis. So sigma ft dt, integral sigma ft dt, or simply say ft dt because we are just concerned with one force over here, is basically nothing but this area under the curve, right? That's integral ft dt from some time to some time can be written as integral t square I hat minus 2tq dt. Okay, so let's say we're integrating this from 0 to some time t. So this will be t cube over 3 I had minus 2 t to the power 4 over 4. So that's actually power 4 2 j hat, right? And that is your linear impulse. And the linear impulse we have seen is equal to change in linear momentum. So that's mv final minus mv initial. So if you know initial velocity, okay, you can find out what the final velocity would be, right? And this allows you to compute the change in linear momentum, which in turn could be used to compute, let's say, initial velocity or final velocity, all right? Now, this isn't anything different from what you have done before. Before, if you had to find the change in velocity, you would compute the acceleration and then you could integrate it, just as we did over here, and get the velocity. So it's not like that we are really doing anything new. We're just looking at this same thing that we've done before in a new light, right? We're saying that on the left-hand side, we have linear impulse. So when you know forces as a function of time, then doing something like this or using kinetics or particles approach to get the acceleration first and then get the velocity is not going to be any different from each other, okay? But where it makes difference is when you don't know how forces change over time, all right? That is, if you don't know what this curve is, really. So if you don't know what this curve is, what can you do? Well, one of the things you can do is you can say that I can compute some average force that may be acting on a particle over time, okay, if I know the change in linear momentum. So let's say I know my right-hand side, all right, and I know that there is a particular force applied on the particle that gives rise to change in this linear momentum. So for example, I say that, well, I know that there is a car and this car was involved in an accident with a truck. Okay, this was involved in an accident with a truck. So this is the car, here is the truck. But we don't know the nature of the forces that acted on the car at the time of impact. Okay, and this is a very short-lived event. Okay, the impact happens and then the impact is gone, right? But the damage is done to the car. But the question is, we want to figure out what is the extent or the magnitude of the force that was acting on the car. And we're not necessarily interested in, this profile, right? How that force of impact is changing over time, because the interval of the impact is so short that we really don't care about this, right? But what we do care about is having some sort of magnitude figure, some estimate of what the force might be. Maybe a lower bound, right? What is the minimum amount of force that acted on the car? Or maybe an upper bound, right? So anything we can get of that sort would be useful. So one of the things we can do about integral ft dt is to write this as some average force times the duration of the event. Okay, so we have to have some estimate of the duration of the event. If let's say this is an impact force, and we'll talk about impact forces pretty soon, then this duration we know is going to be fairly short. It might be in millisecond, maybe 1 millisecond, 2 milliseconds, or 3 milliseconds. And we can estimate some average forces. So what we're saying is that we have a force versus time graph, but we are going to replace this with a force average times time graph, where the average would be some line, right? This is a constant line. So if you extend this to the left-hand side, we have some average. Now, one thing we know about the average of anything is that you have to have some numbers above it and some numbers below it, right? Which means that we know that this average force would at least provide you a lower bound for the forces that change over time, right? So we know at least that much. So lower bound is good too, because we can say confidently that at least this much amount of force acted on the car at the time of impact. All right. So now if let's say we know the change in momentum, so we know mv final minus mv initial, right? We know, let's say its initial velocity was 55 miles an hour and the final velocity is something else, right? So after the impact, maybe the car moved backward at a speed of, let's say 30 miles per hour, and initial velocity was 55 miles per hour. We can subtract these two quantities and we can get the change in the momentum. We estimate what the delta t might be, let's say 2 milliseconds. And then from that, we can compute what the average speed would be, okay? So, sorry, the average force would be. So let's do an example. So let's say we have our car initial velocity was, what do we call it? Let's say this was, 60 kilometers per hour. So 60 kilometers per hour is 16 to 5 over 18 meters per second. Okay. And final velocity is, let's say 30 kilometers per second. So that's 13 to 5 over 18 meters per second. So actually 1 kilometer per hour is 5 over 18 meters per second. So I'm using that unit conversion factor over here. All right. Okay. So directions are important as well. So let's say initial velocity was this way and final velocity is the other way. Okay, going backward. So we have to pick a coordinate system. Let's say this is positive x, this is positive y direction. Then the delta p is mass times final velocity minus initial velocity. So final velocity is some mass times minus 30 times 5 over 18. And then minus initial velocity is positive, so that's 60 times 5 over 18. So that's actually m times, I'll take minus outside, 30 times 5 over 18 outside as well. So this is actually 1 plus 2, right? So that's actually 3 times. So that's minus m times 30 times 5 over 18 times 3, okay? So if you know an estimate for the mass of the car, let's say 500 kilogram or 1000 kilogram, we know this change in linear momentum, right? And this is in kilograms meter per second, right? Because mass and we have the velocity in meters per second. Okay, now we know that this is equal to, F average times delta t, right? Because we are trying to estimate the magnitude of the collision force. So we can write that F average times delta t. Let's say the impact lasted for 2 milliseconds. So that's 2 into 10 power minus 3. equal to minus, now we'll substitute some numbers. So M is, let's say, 500 kilogram, and 30 times 5 over 18 times 3. Okay, so let's do this calculation. So this comes out to minus 12,500. Then F average, and I should write I hat over here because this is a vector quantity, would be minus, so we'll divide this by 2, so that's 6250 over 10 power minus 3 I hat. Wow, this is turning out to be a large number, right? So the magnitude of the average force is actually 6.25 into 10 power 6 Newton, right? And this is the magnitude, so we'll get rid of this I hat, right? That's the magnitude. That's 6.25 mega Newton. That's a very large force that acted on the car. And what we're saying is that this is actually a lower bound, right? So we're saying that this is at least the amount of force that acted on it. In other instances, during the impact, we know that the forces would be higher than this actually.